upstream mechanics. And so, Professor Brown, it's on you.
Well, yeah, Jay, thanks very much for the introduction. I think I'm actually in the wrong room. I'm supposed to be at MSE 402 though, so sorry. No, that was I think probably transcription. Oh, thanks. Thanks for the perfect. Great. Well, yeah, it's great to be here. Great to have, so many students interested in this topic. I think that, you've been hearing a lot of lectures. I've seen some of the other guest speakers, and I know, many of their work. So I know you've seen a lot of things about self-driving labs and how they're used and why they're used. I think there's two things I want to make sure to emphasize today that might be a little bit new to you anyway. One is that 3D printers bring something really amazing to the table because, a lot of what you've probably seen in self-driving labs is based on, in many cases, chemistry. And chemistry is necessary and it's important, but it's also very hard. And so controlling all the different things, to make interesting materials with chemistry is a major challenge. And so one thing that 3D printers give you is just enormous complexity right out of the box. And so they're a really great platform to start thinking about these ideas of what is a self-driving lab and how can we study it. And the second piece is that I want to make sure to cover is kind of reflecting a campaign that we've run that took about 2 years to run. So 2 years of kind of continuous experimentation. And so that's a topic that, a lot of the labs you've seen, I'm sure, are kind of like, okay, we worked for a year and set things up, and then it ran for a week or two, and then we published on that. And that's hard and it's important, and a lot of times that leads to really great discoveries. But what happens when you start running these for years nonstop? And we're starting to see that now. But there's a few key learnings about, so when you have a self-driving lab and it's running by itself, what does that mean? How do you interact with it? How do you drive a self-driving lab? And so those are some of the questions I want to make sure to cover today. It's I know we only have 50 minutes. I could talk for that nonstop, but it's more important to me that this is interactive. So if you have questions, feel free to just raise your hand or jump in. Just a bit of background. I'm going to talk about 3D printing today, but it's worth highlighting that my group does more than that. Really, we're kind of more generally involved in self-driving lab research in all of polymers. And so we have an effort that I'll talk about today that's really in the topic of 3D printing. We also have work in the deposition of polymer films, in which these are applications that span battery materials and PFAS-free coatings, looking at functional composites using AFM techniques, and some work going on currently in kind of pedagogy of how we teach people how to use these techniques. So there's a bit more to my program that I'll cover today, but I just want to highlight that in case there's questions you have after. So what I want to cover today are kind of three different pieces here. You've seen, well, I'm sure every talk you've seen in the series has had a flowchart, right? Like this is a circle diagram of some kind. And so, in these we have robot performing experiments and then algorithm choosing experiments. And I want to talk about kind of three pieces of this. One is kind of how effective are these? How do we know that they're effective? The second is what kind of unique campaigns they enable, and then how they fit into the broader research ecosystem. But to do this, I have to kind of motivate. Jay mentioned that we are working on absorbing mechanical energy, and that's 100% accurate. So I think the one piece when you're thinking about any experiment, but a self-driving lab especially, you need to have a really good reason to do that experiment, like a reason why you, for example, couldn't learn what you wanted to learn here with simulation. And so what we want to study is mechanical energy absorption. And so this is a property that is of utmost interest when you're thinking about things like the crumple zone of a car, where in a disaster, it's converting the kinetic energy of the motion of the car to the deformation, the plastic deformation of that crumple zone, or maybe the padding of a helmet that maybe is functioning more elastically so it can be used over and over again, or packaging and things you might purchase online, or sports equipment. And these are all very different things, right? They all have very different use cases made of different materials, but they do share an important feature, which is they have one kind of common design objective, at least categorically. And that's that their job is to absorb a lot of energy without damaging the thing they're trying to protect. And so what that looks like, I know that a lot of you probably have backgrounds in chemistry, so I want to sort of give you the physics one perspective on what we're trying to do here. And that's that, if we're thinking about kind of like a force displacement curve, we're trying to compress something to failure. What things like foams will typically look like is shown here, where you have a couple of distinct regions. And so what we're trying to achieve here, our objective is to absorb as much energy as possible, which means we need a large area under this curve. And we need to do this without damaging the system we're protecting. So that means there's some force for which we're going to damage it, and we need to stay below that. So like a crumple zone is a good example. If you apply too much force here, the passenger cab will crumple, and that's a problem. So you want to absorb energy without surpassing some limit. And so this is challenging to do. as you might imagine, because we know a lot about some regions of this curve. We know like the elastic region, this we can simulate very easily. Densification, this is when the material's been kind of squished into a puck when there's no air left in it. But this region in the middle here, this is really the problem, because here we have these complex interactions. The material's becoming nonlinear, the geometry is becoming nonlinear. You're having self contacts. So we can't easily predict using simulation what's going on in this regime, and this regime is critically important for absorbing energy. So that's the motivation. How do we predict that? And one thing that we've realized from early on is that a great way to rapidly screen different structures here is 3D printing. And so people have been using 3D printers as a way to make complex geometries for energy absorption for a long time now. And typically these will involve a few tens of experiments or so per publication. And so we said, okay, well, can we use this as a platform, this 3D printing for energy absorption as a platform to study self-driving labs? And so we built this system we built it over the course of about 2018 to 2020. This is, as Jay mentioned, we call this the bear, although at this point it hasn't earned that name yet. Right now, this is just it in kind of automated mode. But what you're seeing is that, it's a collection of 3D printers. These are fused filament fabrication. After the structures are printed, they're retrieved automatically. They're weighed over here, and then they're tested compression to failure using this Instron system. And this happens automatically. We can tune something between about 50 or 100 samples per day, depending on the kind of tests we're doing. And I'm glad, by the way, that Chris Reyes is on the call. He was instrumental in this first work, really teaching us, as you can see down there, teaching us a lot of, and co-mentoring the lead student, teaching us about Bayesian optimization and how to implement that. So I'm really glad he's on the call. So the question, though, is, so we have this robot, it can test things rapidly. What do we do with it? And so, one thing to think about is, well, we have to have some ability to kind of benchmark the progress of this system. So we designed a system that we thought could have some interesting kind of mechanics present. And so this is called the cross-barrel family of structures. And what you have here is 4 parameters. So these are geometric parameters. For example, how wide is a column? How thick is a column? We then put a number of them n in a circle and give them some twist angle theta. So there's 4 parameters here. It means we have about 500,000 distinct structures we can make inside this space. And importantly, these do a lot of different stuff mechanically. For example, you can make these kinds of cross barrels that are brittle. And so from an energy absorbing perspective, this is quite bad. But can also be bad for a different reason. For example, if it's too strong, then if you try to compress it, it never yields. And so you basically hit that force threshold, which in our case was about 4.8 kilonewtons. You hit that force threshold really early. So this is also a bad structure. And what you're seeking are things that look more like this, where you have a yield point. So at some point, you start to bend over, and you have this really comparatively smooth region and a lot of area under this curve. So the question is, okay, can we find these structures efficiently? And so, the first thing you might do in this kind of, parametric optimization is, okay, well, if you're doing a simulation, for example, what you might do is just do a lot of simulations, and so here with the experiment, we say, well, we can do a lot of experiments. So we take this parameter space, which is again, a 4D parameter space, and we can break it up into a grid. And so I'll show you, what these points mean, but basically each of these rectangles is one slice of that 4D space, slice with a constant number of columns and a constant thickness of those columns. But then inside of that, we can have a set of points we choose on a grid. And so we can do these 600 experiments in this grid, and we actually do them in triplicate. So we ask our robot to perform 1,800 experiments, and we can fill in this response surface with an experimentally derived response surface. And so this is, again, building this from these 1,800 experiments. And what you see is that, first of all, it's a complicated surface. You see regions that are blue, these are low efficiency, low toughness, and so they're not good. Regions that are yellow that are good. And another consequence of this is, well, we could say, well, where was the best thing we found? It turned out it was right there. That's our predicted best design. And so in some sense, this gives us kind of a starting point for benchmarking. But as we've talked about, this allows us to, human chooses this grid of experiments, and then we have the robot perform them. This is half of what we're trying to achieve here. The other half, when you make a self-driving lab, is closing the loop using an algorithmic decision-making policy. And in our group, we tend to use Bayesian optimization. I understand you've had a good background about that, so I won't belabor it. But what you have once you couple these two things together is now a closed loop system. So we take now this robotic system that combines these printers and this testing, and we close the loop. And once we've done that, we now can call it a Bayesian experimental autonomous researcher, which is where we get this term BEAR. And so, what we can then do is say, okay, we can run campaigns where we say, okay, starting with no information about this surface, the response surface, find the best structure. Oh, I see there's a chat. Is that a question? No, it's not. Okay. So looking at this, you say, okay, well, our goal here is to find find the highest toughness part, and we have no prior information, so we're going to use Bayesian optimization with an expected improvement acquisition function. And what can allow you to visualize that over here. So this is going to be a random point we start at because you have to see this process somewhere and you have no information at the beginning. And to remind you, this is where, if I get, okay, this point here is where the extensive grid-based sampling found the best result. And again, we are not giving that information to this campaign. This campaign is starting totally naive. And so once we start this, it starts, running experiments, collecting data points. The points here are showing up in the order in which they were collected. You can see a few things happening simultaneously that are worth highlighting. One is that, kind of it spreads out and explores all space. So you're seeing that kind of naturally, this is encompassing some ideas of exploration. But then it also spends a lot of time here where we know it's very good, and actually also over here. And that's kind of reflecting it's balancing also exploitation, where it's trying to find good regions and it's, trying to spend time there. And so having done that, we can say, all right, well, this point here is where this campaign predicted the best result would be, which is not where we found before using the grid-based surface. So the question is, who's right? And, as an experimentalist, and we have a saying in my group that experiment, sample, ground truth. So if you want to find out the answer to the question, who's right, the only way you can do that is with more experiments. And so what we did is we kind of went head to head the results of the best from this, this purely automated campaign and this grid, where after 1,800 experiments, it predicted the value of a point that was about 35 joules absorbed, versus now if we look at this campaign that used 100 experiments, we found that, this surpassed that with only 100 experiments, getting into about 40. And we actually repeated that process, doing that same campaign 2 more times and got very similar results. And, by sampling different points in space, of course. And so this was, shows very clearly that if, you run this kind of system, this will give you accelerate your ability to converge in terms of numbers of experiments. Also, of course, not to mention the fact that automation means you can do them more rapidly and in many ways more consistently. And so this was, I'd say, early days of this field of self-driving labs, and was a piece of benchmarking that I think is important. And we actually kind of built on this both in a review paper that Jay was involved in, but then also in some subsequent work with Tony Benissisi's group. But basically, the idea is showing that, okay, what we can show here is that, in this we're using roughly sort of 30 times fewer experiments than would be required in grid-based searching is an important benchmarking. And to our knowledge, this was the first time that, well, actually Bayesian optimization was used in a self-driving lab, but then also that benchmarking was provided. And I want to highlight, though, that we can't get kind of too hung up on numbers like 30, though, because one of the things that we've done kind of since then, and this was some of our collaborative work with Tonio's group, is that, we really, you can't, there's no free lunch. And so what I mean by that is this great theorem in optimization theory that maybe you've seen before, which is called the no free lunch theorem, which the summary of it is that there's no one algorithm that's the best for everything. There's different algorithms are suited to different parameter spaces. And so if you don't know anything about your parameter space, you can't be sure that, one algorithm is going to be the best. And so here is an example of how we quantified the sort of different accelerations and efficiencies that are present when you look at different algorithms against pre-existing data sets, including our cross barrels, but then additionally some other data sets. And basically, the summary here is that, there's not one best algorithm, which shouldn't surprise you. So, while it's important, I think consistently we've seen that there's, sort of factors of 10 acceleration or so, the right, choosing the algorithm to the given task is of one of central importance. But having benchmarking is important because then people can say, okay, well, this is going to accelerate things, and we don't know quite how much, but we know it's going to be helpful. And so, going from there, I want to go to, a few other pieces of this is that, one factor of this kind of self-driving lab is that we were treating this like a black box. Like we said, okay, we don't know anything about mechanics. Let's let this run, find the structure. But in reality, we know a lot about mechanics, right? We know we can do simulations. Maybe we can't simulate exactly the property we care about, but maybe that simulation can still be useful. And so some of the things we studied following on this were things like, okay, well, can we take simulations of mechanics and use that to sort of accelerate this learning process? And the short story of that is, yes, of course, you can. There's, depending on how close your simulation is to what you care about, that can be faster or slower. If you have a great proxy of what we care about, the acceleration is going to be enormous. Otherwise, you still can improve it, but it's going to require some more thinking. Things like transfer learning to understand how to transform your input space. I don't have time to quite get into the details of this, but this is an important feature that means that these self-driving labs don't need to be the whole ecosystem themselves. They can be a part of a larger ecosystem of translating from prior knowledge to some property you can care about. And on this other side of translating out, well, then the question is well, can you take some measurements over here and move it to something else you care about here? is an impact study, for example, where we were looking at, the impact performance of different lattice structures. And we can't do impact measurements in our self-driving lab, but we can do a lot of quasi-static measurements, and then learning the connection between these quasi-static experiments and impact is an interesting question. So there's like transfer learning questions of how you get that information, moving it over to that related property. And so in this way, you like having a large body of information here still provides a tremendous value. And so I want to highlight this just to say that, this is an ecosystem, right? This is one piece of an ecosystem that can provide huge amounts of kind of knowledge up and downstream. But the kind of main event I want to cover today is really talking about unique campaigns, and this is thinking about, okay, so you have this self-driving lab, and it can do things that it can accelerate research, but I want to focus on accelerating is boring, right? Going a little faster is not going to change the world. What's going to change the world is doing things that you could not do before, doing things that would be totally impractical before with this. And so I'll talk about a campaign that we ran that encompassed about 25,000 experiments of the type I just talked about, and what we learned doing this. And one of the key things we learned is why in this multi-year campaign, you really can't think about this as like one static experiment you set and go, but rather this is now a system where there's a human interaction in this, and the human is not present in the loop, because that would mean that you would require the human to do the experiments, but they're, to use Benji Maruyama's words, they're on the loop. They're participating in this, they're guiding it in some way, but the loop is proceeding without their direct feedback regardless. So let's dive into this study. And so again, what I mentioned before about our motivation here, we want to find these highly absorbing structures. Although what I just showed you in the previous story basically was how if we wanted to optimize one particular case, we had like one family of structures and one material and one force threshold. And what we learned there is it took us about 3,000 experiments to show that we really only need to do about 30 to get to the value we wanted. And so the question that we wanted to ask is, well, can we generalize this to all sorts of other structures? Can we then say we find one family of structures and process that can allow us to answer this across a very large space? We can solve this more generally. And it's clear that if we want to go to a general solution, we have to move away from a very specific shape to very general shapes. And so to this, we kind of identified a cylindrical shell as a mechanical motif that is, of course, widely studied. People study this a lot in the mechanics literature. And because it's, in many ways, it's very simple. It's kind of like a harmonic oscillator of mechanics. But it's also, people, it's being used ubiquitously in nature and engineering, the stalk of a wind turbine, the stalks of bamboo, the rocket shell. These are all, they have this unique features of being able to withstand large compressive loads while encompassing a lot of area inside them. So they're very nice shapes, and they're simple mechanically. They're defined by 3 geometric parameters: their height, their diameter, their wall thickness, and some mechanics, like, for example, elastic modulus and a yield strength. So this seemed like a good place to start, but if you are into mechanics, or if you have talked to people that are mechanicians, one thing you'll know is that cylindrical shells are actually pretty bad mechanical structures in many ways. Like if you look at a cylindrical shell, they tend to buckle. And so buckling, I'll show you a movie of this here. If you're going to see, as I start compressing it, you'll see kind of a feature show up here. This is a buckle. So there it kind of buckles in. And as a result, this becomes a lot weaker. And so the force you take to initiate that buckling process is about 20 newtons, and then it drops to nearly about 10. And that's this whole area here is kind of wasted opportunity from an energy absorption perspective. So the buckling that shows up makes it much weaker. The second challenge with shells, which has been studied very extensively, is this question of what people in the literature call a knockdown factor, which is to say that if you have any sort of defect, this buckling process will happen sooner, and that happening sooner will mean that the whole thing is even weaker than you would expect. And so this is a complicated plot, but the thing to take away from this is if you add a little defect to this structure, the shell, that if you look at this dimensionless stress in this region in the middle here is this kind of like medium length cylinder region. As you add increasingly large defect, these curves drop, showing you that the whole thing is getting substantially weaker. So I won't go into all of the details of the non-dimensionalization here, but all you need to know is that adding a defect makes the whole thing weaker. And so the question is, well, how do we address this? How do we find a way to use shells, because they have all these advantages besides the fact that they're simple? How do we use these shells despite these weaknesses? Well, the first thing we thought of is, okay, let's take this shell and let's try to generalize its shape to add more geometric flexibility that allows it to sort of compensate for these deficiencies. And so we worked with Emily Whiting, who's a computer scientist at BU, to develop what we call the generalized cylindrical shell, which we take this shell and we add a bunch of geometric features to it that are kind of motivated by different kind of mechanics elements that I don't have time to really dive into, but I'd be happy to talk to anyone after who's interested. But basically, there's a lot of different sort of gauges. Basically, we add to this sort of 3 parameters we have at the beginning, 8 more geometric handles to now have what we call a generalized cylindrical shell, in which there's 11 different geometric considerations that we have, which gives us, conservatively trillions of possible structures. So now we've gone from a parameter space that's, 500,000 to now, tens of trillions minimum. And so let's just start exploring this. And so our kind of first effort here was to say, okay, so we have this self-driving lab. Let's study this. We're changing the mass of these structures a lot now. So now we're going to look at not the toughness, but the toughness divided by the mass. So this thing called specific toughness. And we're not just looking at one material either. So we're collecting materials and sorting them by their modulus, how stiff they are. So different colors here are different materials. And what you'll see is this is our first about 2,000 experiments in this space where we're using Bayesian optimization to try to find structures that are very tough. And we're, looking across space to do that. And one thing that kind of jumped out to us as we were doing this is looking and saying, okay, well, okay, if your objective here is to find the toughest structures, then okay, this material up here is very tough. This is materials PLA, which is a more rigid plastic. These down here are these thermoplastic elastomers that are much softer. And as we know, like these are useful. Like we use soft materials for energy absorption all the time because they're in situations where we need small forces. And so this kind of way of looking at the world in specific toughness was kind of suboptimal because it didn't let us say, well, there's value in these structures that are not kind of highlighted by the fact that, that they'll be useful in different contexts. And so this made us turn away from the kind of material or the structural level and into the material level and saying, okay, well, if we want to understand this, let's not think about things in terms of force and displacement, which is what we've been talking about before, but let's think about this as effective materials. And effective materials, we need to define this as a stress versus a strain. And so now we're doing an effective medium approximation. And what we have, if we do that, is kind of two things jump out. Well, one is our use case is going to impose some sort of force threshold. That's where we're going to say we want to have this to be function in some space, like a car might be, tens of megapascals, where, a helmet might be 100 kilopascals or something. But if we look at this, we also know that strain goes to 1. This is in a compressive test. That's when you've squeezed the material to nothing. And so the very most that we could ever get out of a material would be this red rectangle. That's the theoretical maximum energy absorbed. And so it's a number that we can find. And then if we look at a given structure, this, for example, blue, that's going to have something we actually observe. And so we can actually just divide these two things to get what's called an energy absorbing efficiency. And this is a term that dates back to Ashby in looking at kind of how to compare the mechanics of different foams. And so we have this non-dimensional term that basically says how good of a mechanical energy absorber is something at a specific stress threshold. But then the next piece to this is saying, well, this stress threshold was chosen in some sense arbitrarily. And so what we can do is we can choose that, so for example, if we choose that to be pretty small, then the material is going to be in its elastic region. The component's going to be basically too stiff. It's not going to work very well. If we choose this too high, the component's really not strong enough to function in this space. But over here, if we choose it kind of right at this level where we capture this large densification region, this large plateau region rather, this is the just right condition. And so there's a maximum value of Ks at a specific stress threshold. Another way of saying that is that like this is a complicated curve. We can actually understand it by basically 2 parameters. One parameter is sigma T star, which is like, where should this be used? Like, what is the best use case of this structure? And Ks star is how good could it be? And so with this, we can kind of simplify this complicated structure into these 2 numbers. So, and thinking about what we've talked about before, so this is the result we had this, this specific energy absorption. And what we can do is we can kind of move this around to this new space to say, okay, what we actually have here is this, how good the structure could be as a function of its use case down here. It's the stress at which you should use it. And what we can do now is say, okay, well, you want to optimize this because maybe this is your crumble zone up here and this is your helmet pad down here. And so if we can find good structures across this whole space, we can kind of solve this in general. And so what we wanted to do is then optimize what we call the performance envelope. So this cyan line here is showing you if you tell me a stress threshold, how good of a structure can we make for you? And that's this point of this line. And so now we want to do this multi-objective optimization of raising this. And we're going to do it across about 5 orders of magnitude in stress, which is a pretty large amount if you're not into mechanics to give you a sense of what this value is. The value down here, 100 pascals, that's about the pressure that, a quarter, I understand a Canadian quarter weighs the same as a US quarter. So that's a simple metric for all on the call. So 100 pascals. But then up to 10 megapascals is imagine that you have that same quarter on your hand, but now there's a horse standing on it. That's the pressure. That's about 10 megapascals. So there's a pretty large range in pressure. or equivalently stiffness. And so if we want to know like what is good or bad in this space, well, if we kind of compare to the literature and say, well, what have people reported the best kind of additively manufactured structures? It turns out that's on the order of kind of 40 to 50% efficient. Things tend to be more efficient up here because this is where plastic deformation allows you to absorb more energy. The way to think about this is these are kind of single use up here, and these are kind of multi-use down here. But anyway, so this is the the sort of space in which we're operating. And so what we did next is say, okay, let's run this in this new space, and we did about 3,000 more experiments. And what you see is that reframing the problem in this way allowed us to really quickly get over this line pretty much across the whole way. And so we'll talk more about as we go on about sort of this iteration between like doing experiments, thinking about how the experiments were done, then changing the framing of the experiments. But this ended up being a very successful way of reframing the problem. It led us to the point of, okay, well, if we're at the level where we're getting these high values, like where is this going to stop? Like what is the very best that's been seen before? And so looking at scouring the literature and really products, what we found is, okay, so there's kind of two, like if we want to find the very best, most efficient things that have been shown in the past, well, the most efficient synthetic thing we've seen has been this foam by this company, Roacell. It's about 68% efficient, and it's able to achieve that by having just a tremendously flat stress strain curve up to when it starts to densify here at a little over 70%. But actually, the leader that we found in this category was not natural or not man-made at all. It was rather the natural material of balsa wood, which was, in particular kinds of balsa wood, like a kind of a low density balsa wood in an orientation that's specific to the kind of microporous structure. We found that there actually had been some reports of this being as efficient as about 71.8, so about 72% efficient, so extremely high. So this is what we thought of as the sort of world record of efficiency. And so going back to our plot here, we can kind of put some lines on here, like this is the best thing that's been synthetically made, the best thing that's been observed in nature is up here. So the question then is, okay, we were feeling kind of ambitious. This was sort of, I think, 2022 or so. We were thinking, okay, well, should we just go for it? What if we, instead of trying to get above this line across all space, let's just find a way to find the very highest efficiency. And so looking at this, we ran another about 3,000 experiments. And so what you see is that pretty quickly we start moving only just over to these plastic structures that are most efficient. And by some combination of serendipity and really just serendipity, I suppose, and the choice of this space, we're able to get hit this sort of this region right here and capture go above the sort of best synthetic structure reasonably fast in the context of thousands of experiments anyway. And in this, you see is this kind of balance between, it serendipitously finds a region, then it capitalizes on it. Kind of, it realizes something good there, and it kind of really starts to exploit, and so it's building the space. However, as this happened, we kind of spent a long time, butting up against this line, and we were unclear as to why we couldn't proceed. There's no fundamental reason why we shouldn't be able to go above that line. So the question is, why isn't it learning faster? And this led us to sort of look at the learning process itself and to see if there was something that was going wrong. And so looking at this, so one thing you probably have seen a lot of is this is what we call a parity plot, which shows that the y value here is the value of the thing we're trying to optimize here. This is efficiency. Y tilde here is the value predicted by the model. And maybe in doing this, what you'd say is, okay, I'm going to quantify this based upon, say, an r squared, and that's going to show me it's about 0.95. That's pretty good. And so that might be, looking at this, you might say, okay, life is good, or model is okay, so let's keep going. But as we kind of dug into this more deeply, what we found, if we zoom in on this top region, is there actually was a problem. And the problem was, and it's illustrated by kind of showing these crosshairs here. What you see is that we are observing structures that are quite good, sort of in the this high region, but we're not predicting structures that are good. So the model is being very pessimistic at the very top end. And so the reason for that is kind of interesting. It's a property called regressive dilution. And what it's telling you is if you have a situation that is kind of, think about like a needle in a haystack type problem. This is a kind of toy example. If the blue is your ground truth and the red is the experiments you're using to sample it, if your prediction, you're training some model or conditioning some model on these points, it has a lot more data in the haystack than it does in the needle. So it's going to, as a result, kind of undershoot that peak here. And that's going to be a problem because this is where you care about this most. And so, the way to deal with this, there's a couple of ways in the literature. One that's, a turbo, that's a kind of a standard package. And there's one that's called Zombie, made by the Buonasisi group. We did something a little bit custom. The basic idea is you just don't train it on the haystack. You only train it on the needle. And so you basically look at the points that are really good and restrict your training to the points in that regime. And so if we do that, we basically say, instead of training on all of our, in this case, 13,000 data points, we're only going to look at the 4,000 data points near the maximum. And if we look, our R squared value, we went down a little bit maybe, but we're able to actually predict the points and this high region. So this kind of let us sidestep this problem and really zoom in on this point. And so once we do that, we can continue our campaign. And you can see that very quickly we're able to shoot over this line. And we actually are able to get up to about 75% efficiency, really because it's, zooming in on this led it to, kind of really hyper focus on that region and getting to points here, you can see about 75%. And so at the end of this campaign, we did, all told about 25,000 or so different experiments. And, one of the major products of this was what we believe is the most efficient structure ever tested. And so this is, it's got a 75.2% efficient. I'll show you the movie of it being compressed. Maybe I'll show you a couple times. But it's got this really interesting behavior where it plastically deforms at the bottom, and then kind of like the plastic front kind of moves up the structure. And there are these like progressive folds that reentrantly combine. And it has this like really interesting set of, maybe I can play that movie again to show you that process. That's kind of, you do see kind of like a local buckling, but then the plastic deformation allows it to recontact itself and then maintain that strength. And so that's kind of like the way that this problem has been solved by the system. And so this led us to like say, okay, well, can we frame this structure into what people already think about in the context of cylindrical shells? And so going back to, thinking about this as a cylindrical shell, with the two properties people care about are basically how tall is it, in a relative sense, and how thick are the walls in a relative sense. And so it turns out this is in this category of what's called a thick-walled medium length cylinder when you do this normalization. And all of the parts that we found that were really high performing were right in this regime. And so going back to this plot I showed you before, to ask this question, well, how does this overcome buckling, the role of defects and all these things? Well, if we look at where we expected this to be on this plot, it actually is way down here. So it turns out that the way we sidestep this defect dependence is we say, sort of by virtue of the structure, buckling happens way sooner than it should otherwise. We don't have any sort of undesired buckling. And as a result, the plasticity can kind of like come in and resolve that problem. So that's kind of the way in which the system has learned to overcome this kind of long-standing mechanics problem. And we can use a little bit more of machine learning methods to help us understand why this works the way it does. In particular, we can use what's called the Shapley additive explanations or SHAP analysis to say, okay, what pieces of this geometry were most important here? And so if we do this, we find that the things that really mattered the most, for example, were the fact that the top and the bottom had this kind of fourfold symmetry, and then the fact that the top and the bottom had a shift relative to them, and that particular shift had this kind of both a linear shift and a periodicity, and those things were turned out were very important. So this kind of allowed us to understand a bit about why this geometry worked as well as it does. But I'd be remiss if I gave you the impression that we did these 25,000 experiments, and what we got out of this was just one thing, one structure. And in fact, I think it's really important to highlight that when you have this kind of systematically collected data set, an important question is, what else do you learn from it? Especially considering I emphasized this point earlier that experiment sample ground truth. So this is a slice into the ground truth of mechanics in some way, with some biased slice, of course, in many ways. But the point being, how else can we analyze this data? And there's a few things that we've done with this, some kind of holistic mechanics things, trying to draw connections between what types of materials are useful where. But the one I want to highlight to you is kind of addressing this more general design question of well, let's say you come to me and you say, I want to have a structure that has some very specific mechanical performance. How can we find that? Whereas previously a way to do this would be let's simulate it, but we have the ability here to draw from these experiments to do this too. So what we've done in this vein is we've teamed up with, again, Emily Whiting in computer science and her student Sam Silverman to do basically to make a machine learning prediction of the entire force displacement curve. Now, this is something that if you look in the literature, there's tons of examples of people that do this using computational data. They'll do a bunch of simulations, they'll train some neural network, and they'll find some way to predict the mechanical performance. Here, we're doing a similar thing, but we're using experimental data. So we're saying the geometry is our parameterization, the geometry and the material properties are our parameterization, and then our output performance is a force displacement curve. We're training it in this way. So not only can we do prediction of what will this structure do, but also the inverse design. So if you tell me I want a certain force displacement curve, it'll say this shape made out of this material will give that for you. And so what we've been able to realize here is kind of a dashboard tool that allows you to both go both ways, to say I want to dial in a specific shape and then figure out the performance, or vice versa. And so again, this is all trained using experimental data. And we've also done kind of the simple things you might expect when you have the ability to tune mechanics. To say, okay, well, if you want to do things like I want to design a part for some particular application, like I want to absorb some amount of energy without overcoming some force limit. How can I do that? The kind of toy example we explored in this area is the classic egg drop challenge, right? If you drop an egg, can it not break? And here you have a very clear idea of what the forces are you want to not break this egg, so you can do experiments. So this is an unoptimized one, and sadly our egg breaks. And if we use this structure and optimize this, we can not break our egg at a reasonably high height as a way to optimize this. And so showing you this can be kind of a generic design tool for kind of arbitrary use cases. And I do want to highlight, though, that one of the big things we learned from this, and I've already kind of gone through it as I was talking, is what I would call, this question of, if you have this self-driving lab, it's not running by itself. I mean, it is in a sense running by itself. It's choosing experiments and running them, but you are making choices by allowing it to run and choosing things like the parameter space, the surrogate model, et cetera. And as you're going, what should you be doing to adjust that? And so, we kind of formulated our experience in a series of, in this paper, Driving School for Self-Driving Labs, where the question is like, well, what should you be looking at? And what should you be adjusting? So just like in a self-driving car, what are the things you should be looking at? What are the things you do to interact with it? And so, I've already gone through a lot of the ways in which we've done that, but I think it's important to highlight that we've sort of tried to take our understanding of this and put it in one place if you're interested in kind of, this perspective on what you should be looking at and how you should be adjusting it. Yeah, so I definitely want to leave plenty of time for questions. So I'll maybe spend the last 5 minutes just of my talk here talking about this question of, where can we put this in the research ecosystem? And so, the piece here that, thinking specifically about research is that, we know that what we do is inefficient from the perspective of the way that we conventionally do research is that we have, a group of people working together, and their products are papers. And they read papers from other people, they publish papers, and those papers get read by other people. And there's a lot of waiting in that process, a lot of inefficiency in how information is moved around. And one way to think about that is, looking at traffic. This is like, there's a lot of arbitrary stops built into this process. And so the question is, can we use self-driving labs to accelerate this, to facilitate this, to say, hey, like we can directly share data with this strategy. We can have maybe people can give hypotheses to self-driving labs in a way that allows them to do experiments more rapidly. We can sidestep the need for publications in a lot of ways in doing this. And so maybe this would look more like a self-driving car type traffic pattern. This is one where I think people get a lot of anxiety looking at this, but basically what you're seeing is if self-driving cars have control of every detail of the road, they can do things that look chaotic and dangerous, but in reality are safe by virtue of the fact of the level of control and the rapid information change. And so how can we explore this idea? How can we explore making self-driving labs a community resource? The zeroth order thing is to share data. This is one where, all the data I've been showing you today is all available online. You can go to our website, capital.com/data, and you'll find it all. It's all, you can download it, it's all got DOI, et cetera. So I encourage you to play with it if you want data sets. It's been particularly popular and kind of as a benchmarking tool. A bunch of people have used that as well. So that's the very first thing we can do. The second thing is we can share kind of ideas of self-driving labs. This is a few other examples of people that have been doing self-driving labs in the space of 3D printing and mechanics. There's one, some folks at MIT looking at the composition of materials for different kinds of additive manufacturing. There's a group in Spain looking at 3D printing as it relates to impact performance. And there's a group we're working with very closely at Maine that are also looking at mechanical properties and compression. And so the idea here is like, can we share directly the sort of designs of these systems as a way to learn? And the last piece I'll mention is this notion of, okay, well, can we allow other people to do experiments on our self-driving lab in a way that sort of amplifies their impact? And so this was a collaboration we started recently with Jeff Lipton at Northeastern, where they have this style of printing that's really interesting called viscous thread printing, where if you extrude this kind of plastic from this fused filament fabrication system, what you end up with, if you extrude rapidly compared to how fast you move, and especially if the print head is pretty high off the bed, is you get this kind of coiling behavior. And this is called the viscous thread instability. And if you can do this, then perhaps there's a way to use this to make interesting materials. In particular, Jeff has been studying making foams out of this, because you can make structures that are very fine compared to the moves you can make and get really controlled densities. And so the problem with this, though, is that you have a lot of variables you need to think about: how fast you're moving, how fast you're extruding, the height of this, and the geometry of this system. So what we did is, working with Jeff, was we basically said, okay, let's do a few hundred experiments here across this parameter space, looking at different kind of foams made in this way. And that allowed us to make a model. We can say, if you want a specific modulus of homogeneous foam, we can tell you what properties you need to do that. And that allowed them to then take this and say, okay, now if I want to design structures, for example, this is an insole kind of from a shoe that you can design with precise modulus in different places along the shoe. So it's an example a collaboration where, they kind of gave us a hypothesis and we ran experiments and we were able to show data back and forth. So kind of, coupling very directly to the community in that way. Okay, so I want to wrap up so that way there's definitely plenty of time for questions. I think a few things to emphasize. One is, that, it's great to have benchmarking. I'm glad that we don't have to do it anymore. And what we want to focus on now is just making new discoveries with these tools. But I think the fact that the benchmarking exists is important. Maybe most importantly, the kinds of campaigns you can do with self-driving labs are really fundamentally different than ones you could do without it. Imagine, if you were working in a lab and the professor asked you to do 25,000 experiments in mechanics, right? So that would be something that would be impossible, so certainly practically impossible. And so this is something that allowed us to, achieve this, what we believe is world record efficiency of this mechanical structure. And then furthermore, it's important to not think about self-driving labs as like this little isolated thing, but also one that kind of has information they can pull in from the world and produce information that's relevant to other properties, and then also as a community resource. And so two parts to that. One being that I think it's important when you're doing this kind of research to always be very open about it, be open about the data, about the hardware, et cetera. But then also, if you're interested in mechanics in particular and you have experiments you want to be running, then let's talk about that. That's something we're excited to explore. And so to conclude, just acknowledging the folks that did all of the experiments you saw. We've got a great group of people, Kelsey Snap and Elder Gongora, which are the people that have been wrangling the bear. Joshua Wang is the one working on that now, and a lot of support to thank for in making this possible. So thanks for your attention. If there are questions, I saw there's one in the chat, but feel free to raise your hand or jump in. I will do the chat question first, which was, how was the performance of the model on other designs, test data, real world data? So the model we are using here, so I guess when thinking about, there's a lot of different models you could be referring to, Cheyenne. So do you want to maybe, articulate, you want to speak up and maybe clarify your question a little bit?
He says he's referring to the neural net one.
Yeah. Well, so right. So the valid, as part of that study, we did validation of the model, right? We did experiments and of new data, and it had very good performance. I don't recall the precise numbers off the top of my head. But yeah, so that I would say the validation we've done in that one has been primarily, it produces some new design and we explore that and using the kind of mechanics, the kind of in-house system. But so I don't know that we have any other validation for that. But for there, it was we were quite pleased with the validation. Looks like Jay has a question.
So many questions. But I'm actually going to constrain myself to one. One of the things that the graduate students and early career folks may lose perspective for is it took you 2 years to find that material. Can you give a perspective for the number of people hours or orders of magnitude, obviously, saved by using this approach and sort of the magnitude of the problem, right? This seems like it's a big problem. Lots of people have been looking at it. And sort of walk through that, please.
Yeah, I mean, so yeah, that's a great question. I think it's, if you set out to make the most, like, let's say you're starting a new lab and you wanted as your goal to be to find energy absorbing structures. Well, first of all, you'll have to contend with the fact that there is, hundreds of other labs working on that problem. And there are companies that have extremely large depth of knowledge on this, right? And so there's a huge kind of incumbency of people studying this. So it's not like you're pursuing some brand new topic, and every single material that has ever been studied for mechanical properties has been looked at in this perspective, right? Like its efficiency and energy absorbing. So this is like a really big problem, right? And so and I think the way to think about this is like the number of years is the number of years, but ultimately what this allowed us to do is have one student that led this project over the span of 2 years break a world record, right? Which is something that I think, if you tried that any other way would be pretty much impossible. And I suppose this is probably on YouTube, so I'm putting myself out there on this, but I do think that, this is so highly optimized, but it would be, and maybe with this data set, you can find something slightly better, but I think in general, this is an extraordinarily difficult record to beat. And so, the fact that, one person could basically do it with a self-driving lab is I think, is pretty amazing. And, so like that's one piece to emphasize, for sure. And then I guess it's also worth mentioning that like the way we funded that effort is the robot was doing those experiments, but it was also doing some other stuff that I didn't talk about on the side. So like this is, this isn't like 2 years, like only doing experiments relevant to this study. We were also looking at, in particular, looking at helmet pads. And so we were designing helmet pads as part of a sponsored research. So yeah, so I think it's important to note that, the efficiency of this is like, it's hard to compare it to like what use possible otherwise. It's like this provides a new class of experiments that you just could not do in other ways, and new capabilities.
Phenomenal. Let's see, are there any other questions in the chat? Also feel free to raise your hand. Oh, there we go, from Bill.
Okay, can you explain again the regression dilution problem? Why is it important for model to be less conservative and predict higher performance sample? Is it performance of sample unknown until tested, so it doesn't matter what the model will think? I think the way to think about that is so the way that when you're conditioning a model generally, if you think about like a loss function in neural network training or something, or if you're thinking about the way that you tune hyperparameters in a Bayesian optimization, it's trying to minimize, essentially, maximize likelihood everywhere or minimize loss everywhere. And so, it's saying that like I care equally about the error here and over here. And as a result, that you don't. You as the experimenter, you care more about the error in regions that are very good than you care about the error over here. So it's possible with something like loss function engineering, you can kind of get some similar results. But the bottom line is that you don't care unequal. You don't care equally about error in the function. You care about way more here. And so using the training to reflect that is going to be an important feature. And so, the way we did it is basically like deny the model access to the data that we just didn't care about. But you could also do it by finding ways to emphasize the importance of the data in that region as well. But categorically, I think that's the piece. Does that answer your question, Bill? I see a heart, but that could be anyone. That's Jay. Yeah, so okay. We may favor Tonio Zombie. So Zombie's interesting. It has kind of an iterative nature to it that's kind of interesting. I think we were making this around the same time they published that. So we made sure to cite it, but we kind of took a parallel path. As far as Ali's question, yeah, poking the bear, nice. So yeah, Ali's question, trying to understand forward and inverse design, can we use it for finding the right design of a material, not a data set? So yeah, absolutely. I mean, so once you've built a data set, once you build a model to predict this data set, now in principle, it's going to have some guess for the performance of every of the millions and millions of possible structures that exist. And so when you do inverse design, it's not just drawing from the experiments that have been done, it's drawing from all everything it can make a prediction about. So this is very standard inverse design where you say, hey, I want some performance I've never seen before. It's going to do its best to find something that's going to match that. Great. Yes, predictions are useful. Okay, so Chris says could also be addressed by non-stationary kernels. Yeah, that's yes, absolutely. So yeah, kernel engineering is kind of the corollary here to do something non-stationary. That would allow you to, another way of saying I want to like weight the covariances there, the training kind of differently in different places. I think that's definitely possible. I think it's the question that you kind of wrestle with when you're doing this in practice is sort of like what is the right there's none of this is I would say like guaranteed to succeed, right? This is all like we're making a guess based upon some reasonable assumptions and reevaluating it as time goes on.
Okay, we're actually right up on time, and I wanted to take an opportunity to thank you, Keith, for giving a presentation. This was really great. Really, I appreciated the level of the presentation. I think it was just right for the group. And also, so for the students who didn't notice, Professor Chris Reyes from University of Buffalo is also on the line to see this presentation. So you get a sense that you're seeing something good. Oh, fantastic. And we'll definitely be bugging you about this. Keith, thanks for the time. We really appreciated the presentation.
My
We
pleasure. Thanks for having me.
Zoom way.
All right. Yeah, drop me a note on email if you have any questions. Otherwise, yeah, we'll see you next time. Accelerate.
Awesome. Take care, Keith.